Today we are breaking down the Qwen3-TTS technical report from the Quinn team, which just dropped on January 23rd, 2026.
And this is a big one. We are looking at a whole family of models here: multilingual, controllable, and streaming text-to-speech.
Trained on, 5 million hours of data?
Over 5 million hours, yeah. Just a massive data set.
So the big headline, the thing that jumps out immediately, is this architectural split they've done.
Exactly. They've built a dual-track language model that supports two completely different speech tokenizers.
Okay, so track one is the quality track. That's the Qwen3-TTS tokenizer 25 Hz.
Right. A single codebook codec, it uses flow matching, and it's all about high semantic fidelity.
And track two is for speed, the latency track.
The Qwen3-TTS tokenizer 12 Hz. This one is multi-codebook designed for ultra-low latency. We are talking a first packet emission of just 97 milliseconds.
Which is incredibly fast, and the results they're claiming are pretty serious.
Oh yeah. They're setting a new record on the seed TTS benchmark for zero-shot cloning.
And they're beating commercial giants like Minimax and 11 Labs on speaker similarity across 10 different languages.
It's like they decided not to choose between quality and latency. They just built a specific engine for each problem and put them under one hood.
All right, let's really get into the weeds then.
Yeah.
Because this paper, it really frames the whole TTS field as this battle of the tokenizers.
It absolutely is. And if you're an engineer working in this space, you know this struggle. It's a constant tug of war.
So on one side, you've got your semantic tokenizers.
Right. Things derived from models like Hubert or W2VBERT.
Yeah.
They are fantastic at capturing the content, the what of the speech.
So the model understands the text perfectly. The output is coherent.
Perfectly. But it sounds flat.
Robotic.
Exactly. It sounds like a machine reading a script. You lose all that acoustic richness, the things that make a voice sound human.
So that brings us to the other side, the acoustic tokenizers.
Which capture the raw waveform, the how of the speech. But they are so noisy, statistically speaking. Language models just hate them. It's so hard to model that raw acoustic data without the model just generating noise.
So Quinn's strategy was basically, why choose? They built two completely different architectures. Let's start with that first one, the high-fidelity 25 Hz model.
Okay, so the Qwen3-TTS tokenizer 25 Hz is built on Qwen2 audio. That 25 Hz frame rate is key.
And in terms of the tech, what's going on there?
So it's a single code book, but the magic really happens in the decoding. They're using a diffusion transformer, a DIT, with flow matching.
Flow matching has been everywhere in the last year or so.
Yeah.
We see it in image gen. Now it's really the standard for high-end audio.
It really is. It gives you the stability that older models lacked. And they pair this with a modified big VGen vocoder, so you get that semantic fidelity, but also the acoustic richness.
But there's a cost. The paper makes a big deal about the trade-off here for real-time use.
It's the look-ahead bottleneck. That's the term. To get that quality, the model's attention mechanism basically needs to see into the future.
It needs to know how the sentence is going to end before it even starts speaking.
You got it. To get the prosody right, to know if it's a question or a statement, it needs a look-ahead. And when you add up all the latencies, you're looking at about 190 to 320 milliseconds.
Which for some things is fine, but for a real-time conversation, you'd notice that.
Oh, you would. 300 milliseconds is that awkward zoom lag feeling. It's fine for generating an audiobook, but if you want to interrupt the AI, it feels sluggish.
Okay, and that brings us perfectly to the second track, the speed demon, the 12 Hz tokenizer.
And this is where it gets really clever for any system architects listening.
Right.
To slash that latency, they had to completely rethink how they represent sound.
They moved to a multi-code book design.
Yep. Inspired by the Mimi architecture.
So when you say 12 Hz, I'm thinking a much lower sample rate. Doesn't that usually mean lower quality? How do they get around that?
They trade horizontal resolution for vertical depth. Instead of one stream of tokens, they stack them. The frame rate is slow, 12.5 Hz. But for every single one of those steps, you have multiple layers of codebooks.
Okay, so let's unpack those layers. What's in the stack?
Think of it like this. The very first layer, Codebook 0, is all about semantics. Its only job is to get the linguistic meaning right. They even use a WaveLM teacher model to guide it.
So layer 0 is basically the script, the meaning.
Correct. Then you have 15 layers of residual vector quantization, or RVQ, stacked right underneath. Those layers paint in the acoustic details, the prosody, the timbre, all the texture.
Okay, so layer 0 for meaning, layers 1 to 15 for the performance.
Precisely. But here's the absolute game changer for latency. For reconstruction, to turn those tokens back into audio, They do not use diffusion. They use a lightweight causal convenant.
Causal is the key word there.
The only word that matters for speed. A causal system only depends on past and current inputs. It has zero look ahead. The moment tokens are generated, the waveform can be emitted.
And that's how they hit that 97 millisecond first packet rate.
That's the magic. It feels instantaneous.
But doesn't that create a huge problem for the language model?
Right.
Standard LLMs predict one token at a time. If you have to predict 16 tokens for every single time step,
the inference cost would be astronomical. It would take forever. You'd solve the decoder latency, but create a massive LLM bottleneck.
So how did they solve that?
With a dual-track architecture and a multi-token prediction module, the MTP.
Okay, how does that MTP work?
So think of the main Qwen3 LLM as a conductor. It predicts the text and that one crucial semantic speech token. It sets the direction.
Got it.
Then, and this is the key, in parallel, the MTP module generates all 15 of those residual acoustic codebooks at the same time.
So it doesn't do layer 1, then 2, then 3?
No, it does them all simultaneously.
Nope.
It takes the semantic skeleton from the main LLM and instantly fleshes out the acoustic body.
That is really clever. You use the big model for the hard part, the semantics, and offload the text string to a parallel process.
Exactly. It decouples the intelligence from the fidelity, and that's what lets the 12 Hertz model feel like a real conversation.
Let's shift to the training. You said 5 million hours of data. I mean, that is just an astronomical amount.
It is. If you listened 247, it would take you over 500 years to get through it all.
Just managing that has to be a challenge. The paper breaks the pre-training into 3 distinct stages.
Right. Stage 1 is general. You just throw the huge, messy, multilingual data set at the model. The only goal is to establish that basic text-to-speech mapping.
But that data is scraped from the web. So it's going to have noise, background chatter, all sorts of junk.
Which leads to stage 2, the high-quality stage. They filter the data down and do continual pre-training. This is where they clean things up, reduce hallucinations, and get rid of artifacts. This is where the model learns to sound professional.
And stage 3, the paper calls it the long context stage.
And this is so critical. They increase the context window from about 8,000 tokens all the way up to 32,000.
Why do you need a 32K context window for speech? Most conversations aren't that long.
It's all about consistency. If you want the model to generate a 15-minute piece, it has to remember the voice and prosody it started with. Without that long context, you get what's called voice drift.
Where the accent starts to change or the tone just flattens out.
Oh, exactly. The long context acts as a stabilizer. The model can look way back to the beginning of the session and say, oh, right, I'm still this person speaking this way.
Okay, moving to post-training. We hear a lot about DPO for chatbots, choose the better answer. It's interesting to see it applied so heavily to audio.
It's the same idea, just different criteria. They generate pairs of audio, and raters choose the one that sounds more natural or has better emotion. They use DPO to align the model with those human preferences.
And they mentioned speaker fine-tuning as well.
Yes, a very lightweight stage. This is crucial for their zero-shot cloning. It teaches the model how to quickly adapt to a new voice from a short clip without having to retrain everything.
So let's talk numbers. The term soda gets thrown around a lot. Does Qwen3-TTS actually take the crown?
On the seed TTS benchmark, which is really the standard for this, the answer is a pretty definitive yes. The 12 Hz 1.7b model gets a word error rate, or WER, of 1.24 on the English test set.
A 1.24 WER is incredibly low. Where do the competitors sit?
It beats Cozy Voice 3, it beats the original seed TTS, but here's the part that I found genuinely surprising.
Go on.
The 12 Hz model, the one designed for speed with the coarser tokens, actually got a lower word error rate than the high-fidelity 25 Hz model.
Wait, really? The lower res model was more accurate. How does that work?
It seems backwards, right? But the theory is that because the 12 Hz tokens are coarser, each one represents a longer slice of time.
Okay.
So the language model is processing the audio in bigger chunks. It might be helping it capture those longer-term dependencies. It's not getting lost in the weeds of the micro details, so it holds the sentence structure together better.
That's fascinating. Sometimes a lower resolution gives you a better big picture view.
That seems to be exactly what's happening.
And what about multilingual performance? They tested across 10 languages.
Yeah, they went head-to-head with Minimax and 11 Labs, basically the industry gold standards. Qwen3 had the lowest WER in 6 of the 10 languages.
And speaker similarity.
That was a clean sweep. Qwen3 got the highest speaker similarity scores across all 10 languages. A clear win.
The paper specifically called out the Chinese to Korean transfer. What was so special there?
That was a massive leap. Cross-lingual cloning is so hard. Usually if you try to make a native Chinese speaker's voice speak Korean, the accent bleeds through, or the pronunciation is just wrong.
The voice fights the language.
Yes, but Qwen3 reduced the error rate by about 66% compared to Cozy Voice 3. The where, were, are dropped from over 14 down to under 5. It suggests the model has actually managed to disentangle the speaker's unique timbre from their linguistic patterns.
Which is huge for things like content localization. You could have an actor dub themselves in another language.
It's a major step in that direction, for sure.
I want to touch on the control aspect. This is more than just cloning. They're calling it voice design.
Right, and this all leverages the ChatML format. Because at its heart, Qwen3 is a large language model. You can just prompt it. You can write, speak with a warm and encouraging voice, or speak like a terrified whisper.
And it actually works.
According to the Instructee Eval benchmark, yes. It set a new state-of-the-art for voice design, beating specialized models. But the really cool part is how they trained it to do this. They mention a probabilistically activated thinking pattern.
That sounds like peak marketing buzzword. What does it actually mean?
I thought so too, but it's basically chain of thought for audio. We know with text LLMs, if you tell it to think step by step, you get a better answer. They applied that same logic to speech. During training, they would sometimes trigger a mode where the model has to, well, think about the prosody and emotional arc before it generates the first sound.
So it's planning the performance before it speaks.
In a way, yes. It's internalizing the stage directions before it acts, and it seems to make the emotional output much more nuanced.
Okay, finally, long-form stability. We've all heard those AI voices that start strong and then just fall apart.
The curse of autoregressive models. They get stuck in loops or just cut off. But because of that 32K context window we talked about, Qwen3 can generate over 10 minutes of continuous, fluent speech.
And how does that compare to the systems that just stitch sentences together?
Those are the chunk-based systems, and you can always hear the seams, right? Those weird pauses or tone shifts.
Yeah.
Qwen3 generates it as one single thread. And interestingly, for these long-form tasks, the 25 Hz quality model actually did a little better than the 12 Hz speed model.
Oh, why is that?
The idea is that for those very long durations, that extra semantic resolution helps keep the model on track. The fine-grained detail provides better stability over a 10-minute span.
So if I'm building a real-time bot, I use 12 Hz. If I'm generating an audiobook, I use 25 Hz.
That seems to be the exact deployment strategy they're recommending.
So to sum it all up, Qwen3-TTS seems to unify three things that are usually totally separate systems. Zero-shot cloning, cross-lingual transfer, and that granular voice control.
And it's all in one framework that supports streaming. It's not a patchwork of different models. It's one cohesive system.
Maybe the most important part for a lot of people listening.
It's open source. They're releasing the 0.6B and 1.7B models. And crucially, both the 25 Hz and 12 Hz tokenizers, all under an Apache 2.0 license.
That is massive. We're not just talking about a proprietary API. This is code you can download and run yourself.
It really democratizes access to this level of speech synthesis. I fully expect to see this in open source assistants and all sorts of creative tools very, very soon.
I just want to leave our listeners with one final thought on that thinking pattern feature. It really feels like we're moving past models that just read text.
It's the difference between reading and acting.
Exactly. The model is analyzing the intent behind the text to decide how to perform it. And if these speech models are starting to think before they speak, to nail the prosody, how far are we from a model that understands the emotional subtext of a script better than the person who wrote it?
That's the next frontier, isn't it? When the AI becomes a director, not just a voice actor, when it can imply sarcasm that isn't written, or add a hesitation that sells an emotion.
We're getting very, very close to that reality. It's an incredible time for audio AI. That wraps up our deep dive into the Qwen3-TTS technical report. Thanks for listening.
Thank you.